Okay, so it's time for starting. The second speaker is Pia Barchandani from Princeton. He is going to tell us about semiclassical kinetic theory of integrable systems. 50 minutes for talk and 20 minutes for discussion. So please start.
Okay. Hello, everyone, and thank you for inviting me to speak at this nice workshop. It's a shame we can't all be at ICTS in person, but it's still nice to see some familiar faces over Zoom. So I'm going to be talking today about some recent work of ours on the hydrodynamics of Collagio particles. I was going to focus my talk to some extent on the hydrodynamics of integrable systems, but this has already been covered very well by others, including Joel Moore, Romain Vasseur, and Jacopo Donadis. So instead, I'll try to bring out some motivation from the perspective of integrability breaking in traps and just how we understand that in some simple cases. And I'd like to thank my collaborators on this work, Shangyu Cao at ENS, Manas Kulkarni at ICTS, and Joel Moore at Berkeley, and in particular Shangyu, who's responsible for many of the beautiful classical simulations that you're going to see. Okay. So the motivation here is to understand how external trapping potentials can weakly break integrability. So that's one strand of motivation. Another is using the recently developed hydrodynamics of quantum integrable systems to understand classical ones. So this is motivated by the fact that writing down the hydrodynamics of classical integrable systems is less obvious than one might think. It's actually quite hard to keep track of all the excitations that one needs to account for, and somehow semi-classical limits provide a method of doing that automatically. And finally, one finds that the resulting hydrodynamic equations for classical integrable systems actually shed light on dynamics and transport within these classical systems that in a way that maybe one might not have guessed without having this hydrodynamic formalism to work with. So with that motivation, let me try to get across the flavor of this problem of integrability breaking in a trap. So the original non-thermalizing system, which I think triggered a lot of the interest in non-ergodic dynamics, made people aware that non-ergodic dynamics was possible in systems you might expect to be thermalizing, was the chain studied by Fermi, Pastor, Ulam, and Singu. So this is just a simple anharmonic chain. They expected ergodicity for non-zero anharmonic couplings, but didn't see this. In fact, in the windows of energies they looked at, they saw perfect revivals at long times, or at least near perfect revivals that were later found to be perfect ones. Now, informally, there are several ways to understand this lack of ergodicity, and you can say in some sense, with the benefit of hindsight, it seems fairly clear that the system might support non-ergodic dynamics. It's near integrability in several senses. So, for example, its continuum limit can be shown to be the Korteweg-de Vries equation, which is known to be integrable. It's close to a harmonic chain at zero coupling strength. There exist integrable anharmonic chains, which are also close to various FPU models. And of course, there's the KAM theorem, which tells you that weakly perturbed integrable systems retain vestiges of integrability. Now, these are all informal intuitions for why FPU doesn't thermalize, but they are actually all quite difficult to make precise. And I think it's fair to say that some aspects of how the system fails to thermalize are still being debated 50 years on. Now, the reason I bring this up is because mathematically, the Fermi-Pastor-Ulam system has some commonalities with this experiment that has motivated a lot of the recent work in integrable dynamics, which is the quantum Newton's cradle. So as you've already heard in some talks, the idea is just to bounce two quasi one-dimensional clouds of rubidium atoms off each other in a harmonic trap. And like Fermi-Pastor-Ulam, you see no thermalization on accessible timescale. In other words, the system keeps on exhibiting revivals as far as you can tell. And like FPU, this problem is tantalizing because it has several integrable limits. There's the limit of no external trap. There's the limit of no interactions, which is free bosons. There's the limit of infinite interaction strength, which is free fermions. So in some sense, the system is always near integrability, and one would like to make that precise, but again, it turns out to be difficult to quantify. Okay, so how do we understand integrability breaking in the simplest case, which is the classical case? Well, to some extent, this has been understood since the 50s and 60s, but the result is subtle to use. So just to summarize the main idea, if you have an integrable Hamiltonian H0 to start with, add an integrability breaking perturbation, and consider the perturbed Hamiltonian, you find that a torus of the unperturbed Hamiltonian only survives if its frequency vector satisfies these so-called Diophantine conditions. So this is basically a non-resonance condition. It means that the perturbation theory converges to all orders. And one subtlety of this is that the set of Diophantine vectors is actually very pathological. It's Cantor-like, it's nowhere dense. In other words, the set of preserved tori has no interior points. Integrability is only preserved in a sense of measure. I can't look at an orbit and say that this is preserved. It's a statement about orbits on average. So this is maybe motivates the viewpoint that KM is somehow not very useful for physicists, even though it's invoked a lot in these contexts of weakly broken integrability to explain what's going on. It's actually, in some sense, it doesn't tell you very much. So for example, it only yields a sufficient condition for tori to survive. This is to say that the bounds in KAM theory are very far from being optimal. A torus might survive, and you just can't capture that within the usual formulations. So second, the set of good frequencies, as I already mentioned, is highly fractal. And what this means is it's impossible to tell with finite precision if any given torus is preserved. And this is maybe one reason to look at any kind of numeric with skepticism. It's just, it's very difficult to tell whether something is genuinely chaotic on the accessible timescale. Now, another issue, which again is not always appreciated maybe in the physics literature, is that KAM actually doesn't tell you anything about a class of systems that we as physicists are very interested in, which is to say perturbed harmonic systems. Now, that's not to say you can't apply KAM theory to Fermi-Pastor-Ulam or the quantum Newton's cradle. It's that you can't take the harmonic trap or the harmonic chain as a starting point and use KAM theory, because actually these systems are degenerate. So the conventional understanding is they form a resonance immediately, but as soon as you switch the perturbation on, but we know that's a little too simplistic. I mean, you can simulate a perturbed harmonic system and see very regular behavior, for example. And a final problem with KAM is is that the proof does not appear to generalize to quantum systems. So let me qualify that by saying I don't know how to generalize it to quantum systems. It seems to me that a basic difficulty is action variables in quantum mechanics fluctuate. So the kind of perturbation theory you do in KAM doesn't seem to work.
Can I ask a question?
Yeah, sure.
But it's also true, as far as I know, that KAM theorem is basically useless for many body system, no? Because this the radius of convergence basically shrink exponentially in with n, no?
Yeah, indeed. So sorry, wait. Yeah, so this epsilon, if you like, also contains a factor of the supremum of the interaction. So indeed, if the interaction is extensive, KAM says that integrability is not preserved at all. But this, I think, is covered by my first point, that it's only a sufficient condition, which is to say that it's far from optimal. So I would say that actually the many-body scaling of KAM is not understood. No one's really studied it in detail. There's one paper from the 90s which, you know, attempts to really tighten those bounds, but it's a very hard problem.
Okay, thanks.
Yeah. Okay. Yeah, so this is classical integrability breaking. And now for quantum integrability breaking, it's pretty poorly understood in general. There's no result like the KAM theorem. One circumstance in which you can get some physical intuition is the three-body problem. So there's a nice paper by Austin Lamacraft from 2012, which works off Sutherland's insight that a natural way to think about integrability is this kind of geometrical optics approximation within scattering. So there's this very nice plot from his paper depicting basically how scattering in the three-body problem works when you have integrability. And the key idea to get these plots is to switch to what's called the reduced three-body problem. And there's a coordinate system in which the dynamics minus the center of mass reduces to a plane and has this six-fold symmetry. So once you reduce the three-body problem to this planar problem, you can show, as Lamacraft did, that the integrability breaking has the physical interpretation of diffraction. And in particular, the amplitude of the diffracted wave is proportional to the violation of Yang-Baxter. So in other words, this colorful plot that you have here breaks up into the wave fronts broaden diffractively, and that is broadening is proportional to violation of Yang-Baxter. Now, it would be nice if one could apply this kind of intuition to the quantum Newton's cradle. And so this was something that I worked on during my PhD, was just looking at a small quantum Newton's cradle, say the three-body case, and actually try to simulate it directly with exact diagonalization. And what you find numerically, just truncating the spectrum for say a few thousand modes in this three-particle sector, is that the spectrum is nowhere near what you might think of as universal integrable or chaotic behavior. It's very far from being Poisson, it's very far from being GOE. If anything, it looks like a very weakly perturbed harmonic oscillator. Now, unfortunately, you can't really adapt the diffraction picture I just described because the wave functions are no longer plane waves at infinity, they decay. So you need to try something new if you want to try to explain this regularity. So yeah, that plot I just showed, if one subtracts off the oscillator energy levels, one finds there's a great deal of regularity in the spectrum. And in particular, we were able to come up with a semi-classical approximation that seems to capture the infimum of the quantum spectrum within the accuracy of the plot. And I'm just going to explain this result because I think it's relevant to the hydrodynamics of trapped integrable systems in general. So the starting point is to look at the beta ansatz equations and try to interpret them semi-classically. So for example, one can write down the beta ansatz equation for the Lieb-Linegar model, which tells you that momenta essentially are quantized with a correction due to phase shifts. And by writing this as a kind of perturbation of non-interacting action variables, you see that the beta equations can actually be viewed as a version of Einstein-Pilloin-Keller quantization, but instead of having integer indices at each collision plane, so normally when you do this WKB or EBK story, if your particle hits a hard wall or a soft wall, or you have to impose a different, what's called a Maslov index. And one way to understand the beta equations is that they arise from a fractional Maslov index at each collision plane. So in this sense, beta ansatz can be viewed as a kind of exact semi-classics. So this gives you a starting point for thinking about the quantum Newton's cradle in a trap. Now, unfortunately, as soon as you add a trapping potential, the beta ansatz formalism becomes invalid, and therefore so do the semi-classical equations I just described. But nevertheless, you can pretend that they work and simply proceed with fractional Maslov indices at each collision plane, plus the usual semi-classical quantization of the oscillator. And once you do this, you run into the difficulty that you don't know what the classical orbits are anymore. So this is exactly the problem that Gutzwiller's trace formula was trying to address. I mean, how do you, when you quantize a non-integrable system, how do you correctly weight the classical orbits? And we weren't able to tackle this problem for the Newton's cradle in general, but did find one tractable case of circular orbits, which had a well-defined normal momentum to the collision planes everywhere. And this is what yields this semi-classical red line that seems to match the numerics so well. So the point I really wanted to make is that the current kinetic theories of the quantum Newton's cradle are in a similar regime of approximation, in the sense that you are pretending that when you introduce a potential, the phase shift structure is unchanged. And so in the sense I've just described, this is kind of like semi-classical quantization. And it would be one thing, it would be very interesting for me to understand is how far corrections to semi-classics are related to corrections to this hydrodynamic formalism. So that's not something we made a great deal of progress on, but as I'll try to illustrate, the Collagera model might be a nice test case for studying these kinds of corrections. Okay, so with that appetizer, let me return to hydrodynamics. So one point to make first is that this phenomenology also happens in classical integrable systems in integrability breaking traps. So they can also behave very non-ergodically in various regimes. So here are some Poincaré sections made by Shang-Yu for a two-body problem of respectively the Collagera model and the Toda model in integrability breaking traps. And you can see that in the Poincaré section of the Collagio model, there is seemingly no evidence of chaos at all. So different orbits and color-coded here. Whereas in the Toda problem, a single chaotic orbit seems to fill, those black dots seem to fill most of the phase space. So you can already deduce from just the two-body problem that the Toda model in a trap is far more chaotic than the Collagio system. Now, some of the references I quoted above also identify strongly non-ergodic regimes in Toda. That won't be the focus of my talk so much. And another curious finding, so the lower part of this plot, is that you can't even discern a Lyapunov exponent in the Collagio case. So all this shows is the separation of nearby trajectories and how it's changing in time. And you see for the Toda lattice, you can extract a linear increase, but not so for Collagio. Now, for the reasons I just mentioned regarding KAM theory, it's impossible to deduce from this plot whether the system is has ergodic regimes, because anything that one plots is a set of measure zero. And so you can't deduce anything about generic chaoticity properties, strictly speaking. But it seems fair to say that qualitatively, the Collagio model is very robust to integrability breaking. Okay, so back to hydrodynamics. Well, hopefully the previous plots have made clear that weak integrability breaking by traps leads to rich physics, which still continues to pose a theoretical challenge. One motivation for the advent of generalized hydrodynamics was actually to describe this dynamics in the large. So for an up-to-date review on this, I refer you to a recent review by Alvise Bastianello, Andrea De Luca, and Romain Vasseur. And these theoretical advances given on the large-scale dynamics have motivated a resurgence of interest in quantum Newton's cradle experiments. So the initial foray 10 years ago generated a lot of excitement, but subsequently there have been several more experiments verifying this phenomenology in different settings. So there's a nice review by Isabelle Bouchoul and Jérôme Dubai on their efforts in this direction. Now, I will say it seems to me that to probe these theoretical questions of chaos and equilibration, classical systems seem cleaner for now. That's not true in general. There are definitely cases where quantum integrability breaking is maybe easier to understand, but the trap problem seems subtle enough that classical physics is easier. Okay, so with that extensive motivation, let me now move on to the main topic of my talk, which is the kinetic theory of Collagio particles. So the background here you've heard several times at this point. The basic ingredient in applying the generalized hydrodynamics formalism for integrable models is a kinetic equation for the single quasi-particle distribution function. So we call this the Bethe-Boltzmann equation. Its velocity is dressed essentially by semiclassical time delays. Now, given that Wigner's formula for the time delay is semiclassical, one might ask why this equation works so well. Well, I would argue one explanation is this interpretation in terms of exact semiclassical quantization that I discussed above. So in some sense, the semiclassical phase shifts are capturing the spectrum exactly. And I should mention that rigorous justification for this equation is increasingly available. Okay. Now, as soon as one puts the Boltzmann equation in a trap by adding a force term, so it becomes unclear that the forcing and the collisional kinetics I just described commute. So this is the same statement I made above when semi-classically quantizing the three-body problem. The idea is just the trap interferes with the simple phase shift kinematic model. So to some extent, this formula is still a conjecture to be tested, even though it works very well. I should clarify, it works very well for experiments, works very well against numerics at short times. But this deeper question of does the system ever really reach equilibrium in all cases? How long does it take to reach equilibrium? Does hydrodynamics break down at some point? So these questions around thermalization, I think, are still relatively unclear. Now, one interesting test case for all of this is the Collagera model, because it has this very unusual property of remaining integrable in certain traps. So here we have a Collagero Hamiltonian in a harmonic trapping potential, also known as the Collagero Moser model. And this is known to be integrable with perfect revivals, both classically and quantum mechanically. So what that means is, classically speaking, all the orbits are described by the same frequency omega. Quantum mechanically, it has an integer spectrum. So that's a quantum way of saying perfect revivals. And so this is quite a non-trivial test case for the naive ansatz of quasi-particle kinetics plus Boltzmann forcing, because whatever equation you write down had better respect this property of perfect revivals. So to test whether this is satisfied, we first need the quantum and classical hydrodynamics of the model. So let me just briefly summarize how this is derived. The main ingredients are the differential phase shift, which is an input to the quasi-particle energies. And that in turn decides the Fermi factor, which tells you the density of states. So yeah, to the experts, this will all be painfully familiar. At this point, it is fairly algorithmic going from all of this data to the hydrodynamic description. So one can try to do this with the Collagera model. So because we'll be taking semi-classical limits later, I'm keeping h bar in the equations. The differential phase shift for Collagero turns out to be just a delta function. And this leads to quite a dramatic simplification in the sense that these complicated beta integral equations that one must usually grapple with to do generalized hydrodynamics become algebraic equations. So this is in some sense the simplest non-trivial case of generalized hydrodynamics, because dressing of energy and momenta just become a prefactor. Even though there are interactions and they are changing the equations of state and so on, in terms of the dynamics, the group velocity is just the same as it would be for bare particles. So this is quite surprising in a strongly interacting model. And what it implies is that the kinetic equation describing quantum Collagero is what's usually called in condensed matter just the freely streaming Boltzmann equation. So for example, if you open Ashcroft and Merman solid state physics, this equation will be there describing free electrons. What's quite surprising is that you started from this inverse square interaction system and ended up with
Javier, can I ask a question?
Sure.
I'm wondering if this Collagero is integrable in the sense of beta ansatz, because I remember that Howden-Shastry chain, which is pretty much like discrete analog of Collagero, is not really beta solvable. I mean, it is integrable, but not in the sense of beta ansatz. So I'm wondering in this Collagero case. And if it's not a priori obvious if GHD could work for that, not bad solvable.
Well, actually, I don't think there are any issues with long-range interactions. So the reason being that you have Sutherland's asymptotic beta ansatz here. So
sure.
that, I believe, is known to be exact for the quantum Collagera model. And as far as I understand, asymptotic beta ansatz is kind of the only ingredient you need for GHD. It means you don't actually have to care that the interaction is long-range because the asymptotic scattering is still described by this simple semi-classical picture. So, so that's how I understand it.
Okay, thank you.
Okay, so this kinetic equation actually has this non-trivial property of perfect revivals in a harmonic trap. And in hindsight, it's maybe the only thing it could be, because if you have perfect revivals in a harmonic trap, it means that your kinetic theory in position and momentum space, the characteristic curves have to be ellipses all of the same frequency. And it's very hard to see how that could happen in anything other than in a free system. So this is a nice sanity check on this force term. Now, I should also mention that the Collagio model, its hydrodynamics has been studied before within the framework of collective field theory. So this is a kind of zero temperature hydrodynamics. The study was initiated for the Collagio model, I think, by Abanov and Wiegmann. And this theory that we've derived can be understood as extension of the earlier results to non-zero temperatures, but in the dispersionless limit. So in that formalism, if you take away dispersion, things become relatively trivial. It's just a free equation. But as we shall see, this seemingly free evolution hides some complications. So that's the kinetic theory of the quantum Collagio system. Now, to really verify this microscopically, it's much easier to start from a classical equation. So for this, we follow the prescription that we developed for the Toda lattice, following some earlier works from the 80s on its semi-classical limit. And by adapting those kinds of arguments, one can derive the semi-classical kinetic theory for Collagio in a controlled way. So you set the classical momentum to be h bar times the wave number, and then take h bar to 0 with a fixed momentum. The semi-classical phase shift again turns out to have delta function form. Now there are various wrinkles here, so you need to cancel entropic factors to prevent a divergence of the free energy as h bar goes to 0. In ordinary statistical mechanics, these entropic factors are actually what help you avoid things like the Gibbs paradox. But in this case, it's best to cancel them to get a well-behaved semi-classical limit. And one thing for the experts is that the semi-classical degrees of freedom that control these beta integral equations actually have slightly unusual scaling with h bar. So naively, a lot of these things look as if they would diverge as h bar goes to 0 or go to 0. And the origin of all of these paradoxes is that when you take the semi-classical limit, you're essentially scaling the quantum momentum space by 1 over h bar. But at the same time, you want to keep the density of physical particles constant. So what this means is that you're actually allowing the total density of states to diverge as 1 over h bar, whereas the density of occupied states is an order 1 number that goes into your hydrodynamics. So this is just to say, as you would expect in the semi-classical limit, some features of the beta ansatz become pathological. But once the dust settles, you get just a classical free Boltzmann evolution, exactly analogous to what I just discussed in the quantum case. So a natural question is does this semi-classical kinetic theory actually work? And at this point, we have tested it quite thoroughly in 2 microscopic classical models using this standard 2 reservoir quench initial condition. And the left plot here is the Toda lattice. The right plot is the Collagera model. Notice that for Collagera, you need to introduce some confinement to do this check, because otherwise the particles will simply fly off to infinity. But you find that the semi-classical kinetic equation at least predicts the evolution of densities seemingly perfectly in the ballistic scaling limit. I should mention some related work, first on the semi-classical hydro of the Cinch-Gordon model by Alvise, Bastianello, Benjamin Doyon, Gerard Watson, Takato Yoshimura. There's also a way to get the hydrodynamics of the Toda lattice from purely classical arguments. So for that, I would refer to a very extensive and nice recent review article by Herbert Spohn. One thing to mention is that it's not clear to me whether one can actually derive the kinetic theory of the classical Collagero model we just saw by purely classical arguments. Now, the reason for this is that if you study the 2-particle kinematics, the dynamics is actually very singular. The phase shifts are very singular. And so it seems to me, at least in this case, the semi-classical limit might be a much more efficient way to get to these hydrodynamic equations. But once you have these, sorry.
May I ask one question? Sorry.
Yeah.
So for the classical case, there is a kind of argument to derive something like a GHD equation by using modulation theory, right? And in that case, they use soliton theory. And my question is whether you know if there are soliton solutions for classical Collagero systems or not.
So I will be describing some of those later on. I don't know if they arise for the unconfined Collagero model. But they do arise in a harmonic trap. You have soliton-like excitations.
Excitation. You mean also classically? You know,
yes.
So for the equation. Oh, I see.
Yeah, but okay. So for example, the Toda lattice has both solitons and phonons.
Right.
The generalized hydrodynamics, I believe, can be formulated entirely as an evolution of the phonons, and somehow captures the solitons. Yeah, then this is a slightly tricky question. So this goes back to what I was saying earlier about.
Maybe, so I just want to add a comment that even for the unconfined Collagera case, there are soliton solutions. But yeah, so we know the soliton solutions even for the unconfined case. But then how to use that further, that I'm not sure. But if you have Collagera on a free Collagera model on a straight line, in the large N limit, you can write down the soliton solutions, analytical forms of the soliton solutions.
I see. Thank you.
Yeah.
Can I? Sorry. Just another comment for the Toda. see the scattering as coming from the particles themselves, right? When
Yes.
seeing the Toda model as particles. Is there
Yeah.
something similar here?
So that's what I was just referring to. I'm not sure. So I tried to do the calculation here for just the two-body phase shift, and the kernel seemed very singular and difficult to resum into just this simple semi-classical delta function.
Right, so it doesn't give this nice simple result.
Yeah, it's not so. So in Toda, you can really write down the two-particle dynamics and extract this phase shift just by looking really at the time delay. And I did try to do this for Collagera at some point, and found something very singular that one could maybe try to expand as an asymptotic series, but was unable to resum that into a delta.
I see, that's interesting. Thanks.
If you have any thoughts on that, I'd be.
I haven't, but yeah, thanks.
And okay, and then in reference to the previous question.
Just one question, if I may.
Yeah, sure.
So the Toda model is in some sense special, one of the special models among classical integral models, because you can also interpret it as these dynamics of particles, right?
Yeah.
And it's in this basis, in the Toda particles, that you can do TBA-like equations.
Yeah.
And if you do classical integrability that was mentioned, if I do inverse scattering, I will get the spectrum that consists of the continuous spectrums of phonons and then also discrete spectrum solitons.
Yeah.
And you cannot reproduce these classical equations that would TBA-like equations that would involve solitons from the semi-classical limit, right?
No, exactly. From the semi-classical limit, they seem to gap out to infinity, those soliton solutions. But the curious thing here is that you can develop a microscopic understanding of this equation, which is seemingly just for phonons, but it seems to be complete in that it captures the whole spectrum of the lax matrix. So maybe what this is saying is that the phonon-soliton distinction is not the simplest way to think about dynamics, and maybe at least for these models, the lax matrix is the fundamental object.
Okay. Okay.
And in fact, the same thing happened for Sinch-Gordon, where you can just use the phonon, and that seems to capture everything you need.
Ah, I see.
In Sinch-Gordon, there are no bound states, right? There are no solitons in Sinch-Gordon.
Yeah, I mean.
So I mean the phonons are actually the complete spectrum if you do inverse scattering for Sinch-Gordon.
Right. Okay. So then it's, yeah. Mm-hmm.
Yeah, but okay. So finally, just to comment the earlier question about using the Witten equations. So that again relies on having some understanding of which soliton and radiation modes are important. And I think the point I want to make is that the semi-classical limit seems to know about this stuff and sidestep it and take you directly to this lax matrix spectrum. So hopefully
so basically just to recap, by taking semi-classical limit, you avoid all these problems.
Yes, exactly. I don't
just
have
get the right degrees of freedom.
counting between radiation and solitons, and yeah. Okay, so these conjectured classical and quantum equations in a trap have the same streaming form, say in a harmonic trap. Sorry, that should be omega, not omega squared. Now this dynamics, it looks like free particles, but when you actually simulate the distribution function of the bare particles, you find they are not freely streaming. So in other words, even though this equation looks free, it's not actually describing the bare particles, it's describing something else. And then the question arises, well, what is doing the streaming? I mean, if it's not describing the bare particle distribution function, what is this equation describing? And there is a clue from our earlier analysis of the Toda lattice, whereby classical quasi-particles are defined via a beta lax correspondence. So I'll explain what that is in a second, but the point is that there are these natural classical quasi-particle degrees of freedom, which is what the generalized hydrodynamics formalism is describing. So yeah, neither clearly solitons or radiation. So working through the details for the Collagera model, putting all the spatial coordinates into a matrix, one can write the Collagero dynamics in this lax pair form. So there are two coupled matrices, which X and L, which intuitively you can think of as position and momentum, and they evolve according to these Newton-like equations in a rotating frame. And the idea is that L is really the fundamental object for the dynamics. So eigenvalues of L label classical quasi-particles. And similarly, the spectral density of L corresponds to the semi-classical density of states. So in a second, I'm going to go a step further and claim that actually eigenvectors of L have a physical interpretation as classical quasi-particles. So let me just claim for the moment that this is what the semi-classical density of states corresponds to. Then without a trap, L has a purely isospectral flow. And by taking the inner product of the X equation in an eigenvector of L, you find that if you like, the average velocity within an eigenstate is just the eigenvalue of L. So the upshot is once you conjecture this beta-lax correspondence to define the semi-classical density of states microscopically, the velocity, the group velocity just falls out from these lax equations. So once you make this identification, this basically amounts to a fully microscopic derivation of the current equation of state. Now, for those familiar with Toda, this step is much simpler than in the Toda lattice. So in the Toda lattice, one can describe rho p exactly, but getting the current equation of state is difficult. In this case, describing rho p is difficult, but the current equation of state is easy. Okay. So how do we generalize this to traps? Well, we can no longer neglect the force term in the evolution equation for the lax matrix. And in fact, the Collagera model is integrable not only for quadratic potentials, also cubic and quartic, but the higher order you go in V, the less tractable it becomes. So the point is that if you attempt to formulate an exact beta-lax correspondence for any specific V, you get something that is too specific. So the most general way we could think of to generalize to arbitrary traps is to really just take this wave function interpretation of lambda literally, say whatever the dynamics is going on, the thing I should call a quasi-particle is an eigenvector of L, even if L is now evolving non-trivially. And so you can write down this expression for the so-called empirical density. And this is what we're going to identify with the thing appearing in the Boltzmann equation. And the intuition underlying this equation is just that the weight of these classical quasi-particles is distributed over all positions. Now, it's made, if you integrate this over X in the case of no trap, you recover my previous expression for the equilibrium density of states. Just to provide some additional motivation for where this picture comes from, at non-zero temperature, the lax matrix is drawn from a random matrix ensemble with a particular structure. And what this means is that its eigenvectors, which we've just identified as quasi-particles, should be subject to Anderson localization with respect to the site index. So for Toda, this is a little more straightforward because the lax matrix is nearest neighbor. So you can argue by standard localization arguments that at non-zero temperature, its eigenvectors should be exponentially localized. But for Collagero, the lax matrix is long-ranged, and what this means is that the localization physics is more subtle. Now, there's some recent work suggesting that even in the long-range case, you should get quasi-particle localization, although it's power law now rather than exponential. And one nice consistency check on this whole picture is that substituting in the empirical density of states I just wrote down, you find the corrections to the Boltzmann equation scale as the commutator between X and L, which essentially measures the amount of real space delocalization of these quasi-particles. So we conclude that this Boltzmann equation within a trap is valid insofar as quasi-particles are localized. So I think that's one step towards understanding thermalization in this system. Okay, so now that we have worked to derive this formalism, let me just flash a couple of applications. So it's known that, as we discussed earlier, the classical Collagio model in a harmonic trap has soliton solutions. Now, these soliton solutions are quite complicated collective excitations, as shown on the bottom right. So none of these particles are passing through each other. It's simply a collective mode which leads to this breathing structure. But if you express this soliton initial condition in terms of our hydro variable and look at the time evolution of our proposed hydrodynamic variable, you see that the soliton dynamics becomes incredibly simple. In terms of this quasi-particle density of states, it's really just a simple rotation of two localized peaks of quasi-particle density. So this is what I meant earlier when I said that these classical quasi-particles furnished a simpler description than any partitioning into radiation and solitons. So that was an integrable application. Now let's look at dynamics in a trap for which there is no reason to believe that integrability is preserved. So let me just elaborate. Quartic potentials are known to be integrable. That means that the first four terms in any potential's Taylor expansion are integrable. It is unknown whether higher potentials are non-integrable, but we see no reason why this particular anharmonic potential should be integrable. Even so, there seems to be no breakdown of hydrodynamics on accessible scales, unlike for hard rods, as Joel discussed a few days ago. So this does raise the question of, does hydrodynamics break down? When does it break down? And it seems that the mechanism discussed by Jacopo et al. And very verified, say, in a Toda lattice, doesn't seem to hold sway here because there's actually no diffusion, as far as we can tell, in the Navier-Stokes limit. So a quick way to see this is just that the velocity is not dressed, so there can be no thermal fluctuations in the dressing, and at the level of linear response, that's where diffusion comes from. So I think I'm slightly over time, so I will just finish there and leave you with some open questions. So what is the mechanism of thermalization here? We think it's coming from these commutator corrections to the free streaming evolution, but it would be nice to pin that down more precisely. our microscopic expression in principle lets you study corrections to hydro at all orders. So one natural question is whether these match the dispersive terms in the collective field theory I mentioned earlier. And finally, there is this striking analytical derivation of the classical TODA thermodynamic beta ansatz by Herbert Spohn using random matrix ensembles. And it would be very interesting to try to do the same for Collagero, although in that case, the random matrix ensemble does not seem to be known. So with that, I will finish, and thank you very much for listening.
Thank you very much for very nice talk. So now the session is open for questions or comments. So if you have a question or comment, raise your hand. Benjamin, please.
Yeah, thanks. Just a simple question. So you say that for potentials up to quartic order, the system is still integrable. So do you see that explicitly in your equations, this integrability up to quartic order?
You know, I haven't thought about it that much, and I was just thinking about it while writing up this talk.
So you should see conservation of our...
Yeah, but I think, so one difficulty is that the lax formalism for these more complicated, so this lax pair that works nicely for no interactions and harmonic interactions. I think to show integrability in the quartic case, you actually need a different lax matrix. So I think this means that the conservation laws are somewhat non-local, maybe.
Yeah, so you would get different type of quasi-particles somehow, and so that description would not be the most clear.
Yeah. So when I said the leanest way to generalize, we didn't want to get into the specification of different lax matrices, so we started just from the non-trapped point. But yeah, good question. I think more can be done there, definitely.
Thanks.
It's okay. So the next, Kinetic.
Yeah, hello. So again, I also have a question about this, what you call this beta lax correspondence, right? Because do I understand it, you use here the M by N lax matrix of the TODA model.
Yeah.
Right. And usually, I mean, if you, the TODA model has two lax matrices, this M by N lax matrix and the 2 by 2 lax matrix. And you can only apply this correspondence with the N by N lax matrix.
Yeah.
Right. And
yeah.
So this will not be applicable to generic integrable models where you only have the basic lax matrix.
Exactly. So there is this extra structure. So it's not, there is this result, right, that every integrable model has the 2 by 2 lax matrix, but the N by N is somehow special. So indeed, both these models maybe admit some simplification.
Okay, thank you.
Okay, so Jacopo.
Yeah, hi. But two questions. So first of all, why in this case the dressing is basically trivial? I mean, it's like eventually it's like free particles, and also like what? I mean, do you actually see thermalization? I missed that. Do you see thermalization?
We couldn't. So okay. So first the dressing. This is so there is first the semiclassical argument. So okay, it's basically the fact that the phase shift is a delta function. So this is the same, I think, as the free boson limit of Lieb-Liniger. You get the same thing. So it's the thermodynamics is actually that of free anyons. So this is a known result that depending on alpha, you interpolate between bosons and fermions.
Right.
And
but then I don't know, because for example, if you take like free fermions and you add a trap, in a sense you are breaking integrability, but you're not, right? Any trap will never never make thermalize fermions.
Yeah, so I think this is an open question. So it was pointed out in the early 90s that the collective field theory of Collagio is integrable in arbitrary traps, but the model itself was only known to be integrable up to quartic traps. Similarly, I think there's a case, I need to double check, I think there's a case that the hydrodynamics is free in arbitrary traps. But yeah, it's not, so yeah, one viewpoint is that these are just anyons in a trap, free anyons in a trap, and therefore integrable, but...
Okay, but of course, I mean, the trap is not local in the anyons, from what I understand. I mean...
Yeah, so maybe that's the issue, and there are other analytical reasons that seem to suggest that quartic is the only, for example, this recent paper by Manus and Polychronikos, I think, kind of
okay, but eventually in the in the data you showed in the simulation, I missed what was the conclusion. So you see some relaxation, but it's not thermalization.
Yeah, so let me just flash those two. So hydro works for all the times you could access. This is on the large scale. And then if you go to the microscopic, so just the two-body problem, I think Shangyu looked quite hard for a chaotic orbit and just couldn't find one. So you can see there's no Lyapunov exponent and all the orbits look integrable. But as does, you know, the reason I stressed the KAM thing was because you can't conclude much from this plot about these subtle questions.
Okay, but how did you check that you don't thermalize? I mean, in this evolution? Well,
as far as we can tell, none of these orbits are chaotic. But maybe we looked at the wrong set.
With the square root. This is with the square root of 1 plus x squared, right?
Yeah.
Okay.
So next, Pavel.
A couple of questions about Collagera, but first maybe terminological. Somehow, you know, in hydrodynamics, you sort of know two descriptions. You know, one is Euler, it's no dissipation, and the other is Navier-Stokes, where you have transport coefficients, and typically really like viscosity, I don't know, thermal conductivity, but you know, but also maybe you may also define self-diffusion. It's more secondary. So what do you mean by the lack of diffusion in Navier-Stokes description?
So the Navier-Stokes was version of these equations was derived by Jacopo, Benjamin, and Denis Bernard, and there is a linear response version of that argument due to Gopalakrishnan, Hughes, Vassar, Khemani, which says that the physical mechanism leading to diffusion is the combination of thermal fluctuations and the velocity dressing, if you like. So it's the way that thermal fluctuations are coupling to the, so maybe I can, so this velocity that I've written as a function of the Fermi factor, the only way this can fluctuate and give you diffusion is via the dressing. But the point is that for Collagio, there's no dressing. So there's no way for these thermal fluctuations to generate diffusion.
But what does it mean physically? You know, for instance, I don't know, you have a passive scalar or something in, you know, in Navier, in liquid. Yes, so you may see that it's apart from, you know, transporting by velocity field, it's also diffuses. Do you mean something?
Well, exactly. So I think, so what I'm saying is if you had a tracer in the Toda lattice at finite temperature, thermal fluctuations would give it diffusive broadening. For Collagio, that doesn't happen because the thermal fluctuations are not coupled to the velocity anymore.
Okay, thanks. And a second question, so sorry, it's not precisely what you are studying here, but again, for instance, if you like, you know, in tradition of classical hydrodynamics or whichever, you typically have an infinite space. People do not talk about, you know, finite, or even, you know, room may be finite, but yes, it's so huge. So I understand that here it's perfectly, you know, reasonable because experiments are done in finite system, and you do with your trap. But for instance, suppose I just don't want to consider any trap, and I consider really infinite system with, I don't know, given initial density, maybe uniform or whichever, so infinite number of particles. So even first, actually, is it well-defined or not well-defined? For instance, Collagera model with attraction, you know, or only repulsive version is well-defined. And another question, for instance, if I do the very same, you know, but not for Collagera and not even in 1D, maybe in 3D, for Newton gas, you know, so with potential, you know, Newtonian interaction. Newton could have done it, but he thought that actually stars would be really stationary. But, you know, after, you know, it was discovered in the realm of general relativity that actually the only solution is like expansion or something like that, you know, cosmological. So it was 20 years after that rediscovered. So in Newtonian cosmology, the only also consistent solution is where, you know, and it doesn't specify any specific point because velocity is linear in distance. So the only consistent solution would be velocity like this Hubble, you know, this parameter depending on t times distance. And so you just write really hydrodynamic equations, the most simple-minded, you know, without viscosity, typically anything, you know, and you just put, you know, this force, you know, from all the system. So somehow, and if, for instance, you also do that with some perturbation, you can find, you know, you can interpret as you know, galaxy formation, you know, more dense part would become more and more dense. So I just wonder, for instance, if you live in your Collagera but infinite world Collagera, probably it's just the same, you know, should be really linearly, you know, velocity should be at any moment linear in distance, you know, and that would doesn't, and but where is the vestiges of this new hydrodynamics? So would it be if we consider here like generalized hydrodynamics, if we consider like evolution of perturbation, or but the major fact is the same, or what? You know, okay, sorry, a very long question.
Yeah, I think you need I think this formalism assumes a finite, a non-zero density background, because in everything we've done analytically, you fix the number of particles, you fix the system size, and then you take them both to infinity simultaneously. It's hard for me to think about having no confinement and
it's also finite density. What I'm talking, absolutely finite density, but you know, system is infinite.
In that case, I might conjecture that this hydrodynamics would still work, but would have to think maybe a bit more carefully about that. Because, for example, it seems to work well for situations like free expansion, where you start with a confinement and you simply let the particles fly apart. But yeah, I don't know if I can give a more detailed answer.
Okay, thanks. And is there really a huge difference between, you know, repulsive and attractive case? It should be, but is there some, I don't know, finite time singularity in attractive case or something like that?
You know, it doesn't show up in the dynamics, but I'm guessing it shows up in the equations of state. So there's probably there's that the pathological point, I think, is going to be yeah, I'm expecting these equations, if you take alpha to be too negative, there is probably a pathology in the thermodynamics, but you don't actually see that in the dynamic equation.
But it was this pathology in the Lib lineager case, for instance, for even finite, as you can see, the finite number of particles, when it was it was something very different, of course, attractive and repulsive.
Yeah. So again, I think the way these hydrodynamic equations are derived, it doesn't affect the dynamical equation. It does affect the thermodynamic equations of state. So.
Okay, thank you.
Abhishek, you have a question?
Okay, maybe I'll quickly ask. So I had two questions. One was like, and for this two-particle Collagero with a square root potential. So I guess it still looks integrable. So is it possible that it's actually integrable, or is there a proof that it's not?
I think this question is open. Yeah, like I said, the intuition is it's just two free anyons, but indeed.
Okay, of course, like I don't know why you chose this particular form, because it's, if you expand them until x to the power 4, it's still integrable, you said, right?
Yes, well, it's hard to, we try to come up with things that were, it's quite hard to, because you don't want something non-analytic, otherwise the simulation is hard to do. Sorry, so you need something with a high order Taylor expansion, but I don't think x to the 6 worked particularly, showed any thermalization either.
Oh, you tried x to the power 6 also, is it?
Yeah, I'm pretty sure Shang Yu tried several things. Yeah.
Okay. So the other question was, I mean, supposing you take the case where you know it's integrable, v of x is, let's say, square or some power 4 or something. So in that case, if you start from some random initial condition, I mean, at long times, does it does it go to some steady state which is described by a GG or something like that?
So again, we could see this for hard rods, but we couldn't see it for Collagio.
So what happens in Collagio?
As far as we could tell, it just continues to follow this free particle-like dynamics.
Okay. It never reaches a steady state, is it?
It's always in a local GG, if you like.
Okay.
Yeah. So this, hydrodynamics with infinitely many conservation laws seems to hold sway all along the evolution.
Okay. Okay, thanks.
Okay, thank you for this time. So, Katsura-san, どうぞ。
Hi. Thanks for the very nice, beautiful talk. And I just have a small comment on the potential. Potential. And the potential is attractive only when alpha, the parameter alpha, is between 0 and 1, right? So actually, the potential is symmetric about alpha equal 1/2. So I guess the negative alpha isn't very physically meaningful.
Good point. Yes.
You can always think of the negative alpha as positive alpha, right?
Yeah, we've chosen the variables so that indeed G is always positive.
Yeah.
So yeah, that's a good point. That so yeah, maybe that question should have was really about negative G, and yeah, I assume that.
Yes, it was about negative G. Yes.
Yeah, and I assume the thermodynamic singular.
So can I interrupt? Since it's time.
Yeah. Okay. Yeah. So, thank you very much.